Hello. So in this video, I'm going to give you a quick walkthrough of the Collab 4 Pytorch tensor from zero to hero notebook. In the first code cell, I import Pytorch, NumPy, and a matplot library. Then print the Pytorch version and check if CUDA is available. This tells us whether we can run computation on GPU or will use the CPU. Next is 0D tensor, which is a scalar, and 0D tensor is scalar, 1D is vector, and 2D is matrix, and then there is like a 3D tensor. How I create a zero dimensional tensor is which is just a single scalar value like 42. I print its shape, which is empty, and its number of dimensions, which is 0. Next is 1D tensor vector, and this cell creates a 1D tensor which is a vector of 5 numbers. We can see here 1, 2, 3, 4, 5 is given. I print its shape which is like torch size, which is 5, and its number of dimensions, which is 1, and the total number of elements using here they should be this. And then next is 2D tensor, which is matrix. Here I create a 2D tensor matrix with 3 rows and 3 columns. I print its shape as a 3 comma 3 and shows its dimension as 2 and number of elements is 9. Next is 3D tensor. This cell creates a 3D tensor which can represent a batch of matrices on RGB images, and its shape is 2 comma 2 comma 2, and meaning uh, 2 rows and then 2 columns. Next is I create tensor directly from Python list, from a flat list, a nested list, and a list of floats. PyTorch, what it does is like PyTorch automatically infers the data type as int 64 for integer, and then for float 32 for floats. Next is creating tensors from NumPy. Here I convert a NumPy array to a PyTorch tensor. NumPy array into a PyTorch tensor from using a torch from here, tensor from NP. NumPy. An important point is that they share the same memory, so changing the NumPy array also changes the tensor. Next is avoiding memory sharing with a clone. This cell shows how to create an independent copy by using torch tensor instead of from NumPy. After modifying the NumPy array, the tensor remains unchanged, proving they no longer share memory. Next is torch zeros tensor, and I create a 3 cross 4 tensor field entirely with zeros using torch zeros. This is commonly used to initialize bias parameters in neural network before even the training begins. Next is torch ones. Here I create a 2 cross 3 tensor field with ones using torch ones, and ones a tensor are used in tension mask scaling operations and initializing certain types of parameters. This cell creates a 2 cross 3 tensor where every element is filled with a value of 3.14 using torch full. This is useful when you need a constant tensor with a specific non-zero value. Next is I create a 4 cross 4 identity matrix using a torch.I where diagonal elements are 1 and all other are 0. Identity matrices are crucial in linear algebra and certain neural network initializations. Next is torch.arrange and torch.line space. So this cell demonstrates arrange for step-based sequence and line space for every evenly spaced values between two numbers. Both are used for creating positions encoding and leaning rate scheduled. Next is torch.random, and I set a random seed for reproducibility and then create a 3 cross 3 tensor with value drawn uniformity between 0, 0 and 1. Torch.random setting the seed ensures we get the same results for every run. Next, here I create a 3 cross 3 tensor with a value drawn from the standard normal distribution using torch.random. This is the most common initialization method to neural network weights. This cell generates a 3 cross 3 tensor of random integers between 0 to 9. So we have given 0 to 10, so it would exclude the 10, and using a random int. Random values of integers are used for creating dummy labels and sampling batch indices. Next is visualize distributions. I plot histograms of 10,000 samples from uniform, normal, and integer distribution using matplot library. This visually confirms the shape of each distribution. We can see here and how they differ from each other. Next, this cell shows how to create new tensor that matches the shape and D type of an existing reference tensor. The like function that we can see here are convenient when you need placeholder tensor with the same dimensions. Next is shape and size properties. Here explore how to inspect tensor dimensions using uh, shape and uh, shape and size and ndim. I also access individual dimension sizes and print the total number of elements using yeah, I can print it using ndim and yeah, numl. And then next is data types and D types. This cell creates a tensor with different types, which is int 64, float 32, and float 16, and bool, and prints each one. Understanding D types is very important because deep learning models almost always require float 32. Next is type conversion casting. I convert a tensor to different types using dot to method and shortcut methods like float and double. Typecasting is needed when mixing question operations between different precisions. Next is this cell checks the default device of a tensor and writes device and then writes a device agnostic code that picks CUDA if available, and otherwise CPU. It also shows how to create a tensor directly into a specific device. Next is moving tensor between devices. Here I show how to move a tensor from GPU to a CPU using 2 CUDA and dot to CUDA and then back to dot to CPU. In practice, both the models and the data must be on the same device for operation to work. Next is I access here, like let's see the 1D tensor indexing and slicing. Access element from a 1D tensor using positive and negative indices and extract the sub arrays using negative indices counts, indexing counts from the end, making it easy to access the last few elements. Next is 2D tensor indexing, and this cell access individual elements of 2D matrix using rows and columns indices. I show how to access the top left corner a middle element and a bottom right element corner using a negative indices. Okay, next is row and column selection. Here I extract the entire row and column from a 2D tensor using a slice notation, and I also show how to extract a submatrix by combining row and column range slices. Next is fancy indexing. This cell selection selects non-consecutive rows using a list of indices and pick specific element by providing separate row and column index tensor here. And fancy indexing is very flexible for advanced data selection. Next is Boolean indexing. I create mm, a boolean mask by applying conditions like a t greater than 0. Then I use it to filter only the matching elements. Boolean indexing is the cleanest way to implement operations like ReLU activation. Next is element wise arithmetic. This cell demonstrates all the basic arithmetic operations like addition, subtraction, multiplication, division, and power. Between two shaped tensors, all the operation work by element without a loop. Function equivalence for arithmetic. Here I show the operations like add, subtract, and multiplication have an equivalent function form like torch.add, torch.sub, and torch.multiply. Both give identical results. The function forms are useful when passing operation as an argument. Next is common mathematical functions. This cell applies mathematical functions like square root, exponential, log, and trigonometric functions to tensor. These are used throughout deep learning. For example, exponential in softmax and log in cross entropy laws. Next is global aggregation function, and I compute global aggregations over all elements of a tensor: sum, mean, standard deviation, variance, min, and max. These are all used for matrices, loss computation, and normalization. Next is dimensions wise aggregation. This cell shows how to reduce along specific dimension using dimension is equal to 0 or dimension equal to 1 using keep dimension and keep dimension equal to true, preserve the original value of dimension, which is important for broadcasting in subsequent operation. Visualizing dimension reduction, I use here like heat maps to visually show how summing along a wait yeah how summing among a dimension is equal to 0 reduces rows and the dimension equal to 1 reduces columns. This makes it clear how the output shape changes depending on which axis you aggregate over. Here I use argument argmax on a batch of classes code to find the predicted class for each sample, and this is the final step of classification, converting raw scores into predicted class labels. Next is broadcasting examples like broadcasting scalar and row vector. This cell shows how a scalar is automatically added to every element in tensor and how a row vector is added to every row of a matrix. Pytorch, what it does is it stretches smaller tensor to match larger ones. Now next is broadcasting column vector. I demonstrate column wise broadcasting by 2 comma 1 shape tensor which gets added to each column of a 2 comma 3 matrix. The key is to reshape the vector to have a right number of dimensions. This cell shows the difference between normal operations that create a new tensor and in place operation using the underscore suffix um, like add. Add in place operation, modify the original tensor and save the memory. Next is view and reshape tensor. I reshape a 1D tensor into 12 elements and 2D and 3D shape using view. The total number of elements must stay the same. The tensor must be stored contiguously in memory. Next is here I use a -1 as a wildcard dimension in view. So Pytorch automatically infers the correct size. The reshape which we see here function is safer than view function. View function because it works even for non-contiguous tensor. This cell flattens a 4D image batch tensor into 1D and also flattens only from dimension 1 onwards to keep the batch dimension. Flattening before a linear layer is a standard step in CNN. Next is unsqueeze and squeeze. So I add a one dimension, I add new dimension into a tensor using a unsqueeze at position 0 and 1. This is used to add a batch dimension to a single sample before feeding into a model. Next is squeeze. This cell removes dimension of size 1 and use of size 1 using squeeze. This is useful after model outputs that have unnecessary extra dimensions or when collapsing a batch size of dimension 1. Next is transpose. Here I transpose a 2D matrix using T. I also swap a specific dimension into a 3D tensor using transpose. Transposing is needed for a matrix multiplication and changing data layout formats. This cell reorders all dimensions of a tensor using a permute, a common use case in converting image data from NumPy HWC format to Pytorch CHW format for processing in convolution network.